Hey everybody, welcome to PC Perspective. I'm Ryan Shrout, joined by Alan Malventano. We're here today to talk to you about Intel Optane again, but this time like a real product.
Like an actual product.
Well, we don't have the product.
Sort of.
Here.
Yeah.
But we got to test a product.
We got to test the product.
So this is the Intel Optane P4800X, which is a fancy name associated with the first enterprise product released using XPoint technology.
I like the name. It's like a crazy workout routine.
P4800X. Yeah.
Guaranteed to kill you.
More than P90.
Yep.
By a large factor. So, you know, we've talked. They kind of pre-announced this a few weeks ago.
They did.
Right.
Yep.
We've talked about XPoint before.
A couple of years ago.
Yeah, it's been a while. So I don't know how much we want to dive into the technology itself. It may be worth kind of giving people who are new or just coming into the idea of XPoint and Optane a quick summary of what it is. And then kind of, again, knowing that we're talking about an enterprise product and not a consumer level product, give as much information as we can about the performance implications thereof.
So the magical thing, or supposed magical thing about XPoint memory in general, is that it's supposed to offer very large gains. It's non-volatile storage, meaning you turn the power off, it still saves everything.
But it's not flash.
But it's not flash, and it has very large performance gains over flash, and ultimately getting you, when this product reaches like its final form of what it comes installed into. This is not what we're testing today.
This is Dragon Ball Z in storage.
Yes, this is sort of like, it's getting you there.
Gotcha.
But it will ultimately result in orders of magnitude leaps in
right, you have that in your story about where they claim 1,000 times the speed and endurance of NAND, but 10 times the density of DRAM, and there was an inherent cost benefit over DRAM insinuated with some of these numbers. To be fair, like this product, the product that we're looking at does not meet those original claims of the technology itself.
Right. The technology itself, like in other words, reprogramming a cell of this, you want to write a byte to it. That can go 1,000 times faster than NAND.
Okay.
What we have to consider is there's a couple of caveats. With NAND, there's some gotchas if you want to just rewrite a byte. Say all of the flash has already been written, everything's full. Flash works sort of like how a CDRW used to work. So if you want to rewrite a small section of a disk, then the disk was already all the way written back in the day. You'd have to read the whole disk into your PC, erase it, and then rearrange whatever you wanted to rearrange and write it all back.
Yep.
And that was incredibly time-consuming.
Painstaking process.
And very painful. Flash memory does a very small version of that. So you write it in pages, which are somewhere around 4 kilobytes.
Yep.
But once you've written all of the pages in a block, which can be on the order of megabytes of the size, you can only erase a block.
So when you say, like, if you want to change a piece of data in that block,
yes,
you have to erase the whole block.
Potentially.
You have to copy the data somewhere.
Copy everything else somewhere else.
Erase the block.
Yep.
Change whatever you're going to change, move it back.
Put everything back.
Yeah.
That's a lot of time wasted.
It is.
Right?
And so, but with XPoint, you don't have to do that.
You don't have to do, not only do you not have to do any of that rearranging, you don't have to do any rearranging at all. In other words, if you wanted to write a byte, you don't even have to take that byte, put it somewhere else, clear it, and write the new byte or anything like that. It's a write in place. You just
change the bit.
Whatever process takes place to do the write, we'll just overwrite whatever is there.
Okay.
So no extra step taken in order to accomplish a write, in other words.
So this means that not only is it's simpler from a kind of management perspective, kind of the controller and firmware, whatever it is responsible for managing things is more simple. I think, the theories we have is that this is not really a controller in the traditional sense.
It doesn't do nearly as much as it had to with NAND.
Yeah.
But the controller still has to do like wear leveling. That's still a thing.
Okay.
You can potentially have a bad spot. It's a lot of memory.
So to remap.
You have to remap stuff out, right? So that can potentially happen. It's not meant to be a huge issue with this, but there's still going to be some spares on any of these devices, right? And just in case something happens.
So part of that, these endurance claims and performance claims are based on the ability or the fact that you don't have to do this rearrangement to write information to it.
That rearrangement is called write amplification when it comes to a NAND product.
Yeah.
And could, it's basically like a factor. So like you want it to be 1. You want it to be whatever you write to it. You want only that much to be how much it has to manipulate on the device. With NAND, that is totally not the case. You have write amplification factors that can go like 10, 20, depending on how, just how arduous the small random writing is to the device.
Interesting.
Yeah.
So, and there's it's also interesting that we don't know, there's a whole lot we don't know about XPoint. We don't know about the chemistry behind the actual
Intel's keeping
chip
the chemistry close to the chest.
itself. We don't know,
we know what the
process
structure
technology it is, or
that's true
anything
too.
like that, right? Like it's really interesting because it is very unique in the industry. It is not a thing that other people have ever created before.
But we can say that like on a die, because they're able to go 2 layers high currently, it is a 3D XPoint technology, not just a planar technology, right? So they're going 2 layers up so far, and on a standard size die, maybe a little bit larger than a NAND die. These chips still look similar on the product, right? So the die is only so big.
Yep.
You're getting 16 gigabytes of non-volatile storage on one per die, which is comparable to NAND.
Okay.
Actually, right?
But we don't know the size of those die comparatively.
Yeah, the die is a little bit bigger.
Is it bigger or small? That type of stuff.
Right.
So that's a little bit of a background, kind of like the technology side. If you want more information on the XPoint tech, Alan has done stories on that in the past.
Yep.
For here, let's focus on the actual product. So the Intel Optane SSD DC P4800X, which is the full name of said product.
Looks just like Intel's other previous NAND-based
it just
SSDs.
looks like a PCIe SSD or a U.2 SSD. Right? This is a 375 gigabyte capacity drive. It is a PCI Express 3.0 by 4 NVMe interface to the machine.
Similar to all prior Intel SSDs.
It's available on add-in card, half height, half length, low profile, and U.2. And then they list some specifications, not a full spec sheet, but they list things like latency, typically under 2 microseconds. 10 microseconds. Quality of service, throughput is listed at IOPS 500 to 550K.
We'll get into that in a couple minutes.
They're listing what I'm getting at is they're listing specs like storage specs.
Oh yeah, these are storage specs.
Right.
Yeah.
So even though it is a vastly and much newer technology than Flash, it's behaving like memory.
Yep. And some of these
like storage.
And some of their specs there, they have like 550,000 random read IOPS, 500,000 random write IOPS.
Yeah.
Stuff like that. And we've seen numbers like that out of other devices like the Micron 9100 Max, which we reviewed a few months back. Intel's own P3700 series doesn't quite go that high, but there are competing NAND products that actually can exceed those numbers.
Sure.
But the catch, as we will find as we go through a review, is that this device is extremely fast without a very high Q depth, which is significant.
Right. So we want to start on the performance side of this, right? Because that's where the discussion.
I would go right to that 4K, 8K page there, and we'll just flip through it. So the first, just looking at the first few charts there, we're looking at 4K random, and just
4K random read.
The way we do our chart, it's the full span. So on the left edge of the chart, it's random writes. On the right edge of the chart, it's random reads, and then everything in between.
So we're doing a percentage. Either side. Okay.
And that's people that want to spec these things out will have a certain percentage in mind for what they're shooting for their workload, so they can just look it up on the chart. Right. We try to make it easy for them. So the numbers are pretty high, but what's significant here is that there are only a few steps taken. In other words, that blue line and then the orange and then the gray and then the yellow. There's only 4 steps worth of Q depth to reach saturation. So this device is going as fast as it can go at a Q depth of 16. Okay. It actually works out to 12 in reality, but we produce our results in increments in multiples of 2. Right?
So if you look at that chart, you'll see blue, orange, gray, yellow, and then this glowing
There's just a blob of all the other Q depths up there.
And it's hard to tell that is actually a combination of your 16, 32, 64, 128, and 256 results.
Which is, by the way, a testament to the consistency of the drive as well, because they are literally all like the same number within a couple of digits.
Okay.
Right? Next chart down, kind of a new thing for us to present, but I'm showing 3 different series of 3 different colors on this chart. And
You're showing QDepth 1, 2, and 4
yes.
for 3 different products.
3 different products.
Yep.
So the blue lines
There's a lot of lines on
the
it,
blue
to be fair.
lines are our new Optane SSD, and then this is going to be consistent through the whole review. So anything that's a green range of lines is a P3700,
which is Intel's fastest NAND-based enterprise SSD.
Yep. And then the gold series there is Micron's 9100 Max, which is their fastest product.
Enterprise SSD.
Grade product.
Okay.
And you can notice pretty much right away, we're showing 3 lines for each of those 2 competing products, and all 6 of them in total fall pretty much all underneath QDepth 1 performance of the new Optane part.
Yeah, with the exception of full read.
With the exception of, no, that's full
I'm
write.
sorry, full write. Okay.
That's full write.
Yeah.
So QDepth 4 writes for the other products were able to exceed QDepth 1 random writes for the Optane part. Now realize when we talk about QDepth, it's how many requests are taking place simultaneously, right? So if you have a database running, there's multiple people hitting the database, multiple people doing online transactions, things that a server would tend to be doing, right? At
QDepth 4, I didn't if you just look at this, at QDepth 4, the fastest non-Optane SSD is the 9100 Max.
Yep.
And it's hitting 140,000 IOPS?
Something like that.
Per second?
And at the same QDepth?
At the same QDepth, the Optane is hitting
270, 280.
280,000.
Yeah.
So 140 to 290,000, right?
So it's easily double, and then we're only taking the reason that these competing products kind of ramp up to the left there is because of the way that a NAND SSD functions. When you go to write something to it, it acknowledges the write almost immediately, and then in the background, it actually does all the work.
It does that write amplification
all the juggling it has to do. It does it
okay.
in the background, right? Which is another complication of what those controllers have to endure to be able to be, speedy and whatnot. Whereas the Optane part doesn't appear to be doing any of that. It doesn't care because it's fast enough that it's just going straight to the Optane. In other words, when you're doing the write, it's going to the cross point during the request, or at least as it appears. Because if it was the other way around, that we would have a curve up.
You'd have a sweep on.
Yeah, they would be sweeping similarly.
Okay.
So that's pretty bold also. It also helps this device with, say, power loss protection, right? Whereas the other SSDs were able to service a write very quickly, so they told you. They still had to do other stuff.
Application.
Yeah. They still had to do stuff in the background. You got to put extra capacitance on those things. You have to make sure that they're able to finish what they started, right? In case the power does go out or some kind of hiccup in the system. Whereas this stuff, if it's going straight to it and it's able to do it that quickly, it's just better overall. And then the next chart down.
This is IOPS versus QDepth.
This is our kind of classic chart of just IOPS versus QDepth. And I'm going all the way out to 256 here because I can. And I just chose, reads, writes, and 70% read / 30% write, just to put 3 lines for each one.
Sure.
And you notice this kind of amplifies it even further. The low QDepth performance of this part is phenomenal. Look at the QDepth 1, 2, 4 there, as it's ramping up compared to the competing products. It's easily double the performance at any of those steps along the way.
Right. Now, the only place where the 9100 Max exceeds the performance of the Optane is at QDepth somewhere between 64 and 128, right?
Yep.
So what is happening there that the Optane drive isn't as fast, or?
So what we're looking at is basically the Optane drive runs into that either 500 or 550,000 IOPS figure, right?
Okay.
And that's basically that controller can only handle that rate of IOPS. Because if you looked at just the latency by itself,
and we think that's a controller, not an inherent limit of
it's not the limit
memory.
It's not the limit of the Optane, because there's a lot of dies in parallel installed onto this device, right? Coupled with, we know that the latency for one I/O is less than 10 microseconds. So if you did all that math and you basically just said, okay, if it was just saturating the bus with that, you'd get way higher than 550,000 IOPS. You'd actually get a full 3.2 gigabytes per second worth of them, which would be on the order of more like 800,000 IOPS, right? Which actually you can see that Micron product is almost reaching. It hits 750,000. That's the max that it hits on that chart, right? It's able to almost saturate its bus with its particular controller implementation. But to get the latencies as low as Intel did, you have to make a controller a different way, right? So there has to be some kind of compromise there. Now, sure, I'm sure like the next generation after this product probably will go even faster, right? But Intel looks like they were going more for the lower latency here than going for the ultimate like maximum IOPS capability.
On this page, I do want to point out the very last graph that shows if there is one area where traditional NAND SSDs may have an advantage.
Sure.
It is on pure sequential writes.
Yeah, that highest line there for the 9100 where it crosses over. And that's at about QDEP 16, and then the rest of the way up. It actually, surpasses the 4800X by something like 15-20% there. But the key is you have to hit QDEP of 16 in order to get there, to see that, right? There's a thing called shallowing the queue. In other words, if you were to put a workload of a fixed amount on both of these devices, if you notice how quickly the 4800 ramps up at such a low queue depth, it would probably be able to plow through those requests and answer them.
And never even get to 16.
Yeah, you can never, the device can never keep issuing them. Basically, you're pulling the plates out from under the stack faster than you're piling them on, right? So if it's able to do that because it's so fast at low queue depths, then you potentially never even hit that mark, right? And then
that's neat. So I want people to go, if you guys are interested in like, for the enterprise geeks out there, if you look at QoS, you look at that type of stuff, it's super impressive. Is there one particular thing you want to show? I'm more interested in showing the bridging the gap section that you had.
So on QoS, we can just kind of sum it up with like one easy chart. Like back when we reviewed the 9100 Max.
Which was the previous fastest enterprise SSD.
To compare that to the P3700, which was the previous fastest before that one, I came up with this test, which was we needed to kind of level the playing field and go, okay, if we're only doing 100,000 IOPS, what does the latency look like, right? Intel actually did a test like this for this product to show it versus the P3700. And they showed us a slide. It's towards the bottom of the QoS page.
Of this page,
Yeah, so they showed us a slide at the event, and I chose to kind of replicate those results. We already had our suite set up to do this kind of paste thing because we've done it before, right? So here is the same chart, but I also have overlaid in the gold lines the 9100 Max, since we also had that data, right? And it, even though 9100 Max is a fast drive, latency still runs at around 100 microseconds versus this, new device, 10 microseconds, literally an order of magnitude faster, right? It's 1/10 of the latency.
So as you look at this, and then again, there are a lot of lines in all these graphs, the best case scenario for the Max, the 9100 Max, is slower than the worst case scenario.
You could call it the worst case scenario.
Or the highest nines.
Yeah, the lightest blue line there is the 5 nines performance. Like 99.999% of the IOs are no longer than this amount.
So that's just telling me that the Optane drive is that 99.999% of its requests are faster than the average request of the 90
of the next
9100
fastest thing.
Okay.
Yeah, which is pretty significant, right?
Yeah.
Yeah. And then what's the other? The bridging the gap.
The
one?
bridging the gap page, I think, is interesting. I know we're kind of like just going through a bunch of numbers here, and it's super interesting tech. But for people who
I just want to do it visually, right?
So we're just for consumers that maybe they're not going to buy this because it's expensive. It's not really built for them. If you want to know what the potential importance of an Optane drive is for workloads going forward, this is the interesting kind of representation of it. If we look at, you're looking at latency percentiles, the data is not necessarily important. It's really the gaps between the drives that matter.
I started off just trying to walk people through it, right? And I said, okay, well, remember back when you had a floppy disk and you went to a hard drive, how much faster that felt? Well, you can look and find the 2 lines on that chart, and you can get a feel for, as you move to the left, that's what that felt like, right? And then if you go down to the, and at that point,
it's important to point out this is log scale.
Yeah, that is log scale. So every time you hit a major increment, it's times 10.
The first graph shows the gap between what is it?
Hard drives, 10,000. That's
hard
a Velociraptor.
drives to DRAM.
Yep.
Right. So the speed of memory in your system versus the speed of the fastest 10K RPM hard drive they had at the time.
Yep.
And then we add in the next graph down, you add in SSDs.
The delta there is 100,000 times the latency.
Yeah.
That's pretty significant. That's why.
This is why SSDs were needed.
Yes.
In general.
Because to get you closer, right? You needed to get closer, right? So then SSDs came out, right? And they started out kind of shaky. Like the first ones to come out weren't the best. They weren't that much faster than like a thumb drive or something like that, or a little bit better. But over the course of, a few years' time, they rapidly kind of gained another, 10 times
10
the
to
speed.
100x.
Yeah.
As we got to NVMe SSDs.
Right. So you got to, and actually what's worth noting is that the solid gray line there, right next to the brown line, you have SATA versus NVMe PCIe. So when you look at QDepth1 performance, which is what we're looking at here, the latency difference is not really that great between NVMe, which people were like, oh, it's supposed to solve everything. It's not. It reduces the CPU overhead so you can hit higher IOPS without saturating the CPUs in the system and whatnot. But it still takes a certain amount of time to read the information from the flash memory.
Okay.
You still have flash memory on both devices. So one might be a little bit faster, but in the end, it only gets you so far, right? So
now the gap between DRAM and NVMe SSD is 1,000x.
Yep. Which is better.
Still seems like
it's better,
great.
But there's still a hole there, right? Optane is supposed to fill the hole. That's what it's for, right? So, and this blue line on this next chart, this is the actual data from the P4800X on this chart. So that's
not theoretical data.
It's not theoretical.
Yeah.
That's where this product gets us today, right? So now it gives you another order of magnitude over, and now you only have 2 left.
So from the hard drive days, we were 100,000 times slower than DRAM.
Yeah.
Now we are 100 times slower than DRAM with this.
Yep.
And then you have one more graph where you put in the RAM disk.
Yeah, I ran
RAM
the fastest RAM disk program I could find. I put on the system just to get an idea of hypothetical, because XPoint is supposed to be able to be put into DIMM form factor. You'd need different motherboards, architectures to support it and everything. But you're trying to get to the point where the other stuff's out of the way, right? Like as it is right now, this stuff is speeds on the order of RAM as opposed to everything else, yet it's trying to communicate via all the standard ways that all the slower things.
The operating system, the software interfaces, that type of stuff.
Yeah, so I just showed, like, here's a RAM disk that was running on the order of like 2.5 microseconds, and that's something that people can actually do today. And you could tell that the Optane part is actually closer to the speed of the RAM disk than it is to a very fast NAND SSD, right? Interesting. So interesting stuff there. And then there's a few notes on the polling versus interrupt thing.
Yeah.
We don't have to go that much into detail.
No,
but
I don't want to do that here.
Definitely read the article on it. There's more hurdles, even in testing, that we had to get past.
The drive is going too fast for standard Windows.
Interrupt requests and things
the way
of that
that they would handle, I/O.
It's not that it's too fast for it. It's just that these other delays have always been part of the equation, but they've been not significant compared to how long the requests took.
If it's a 5% of the delay versus it's 40% of the delay, suddenly it's a bigger problem. So these are expensive. The 4800X, P4800X 375 gig is a $1,500 device, so it's about $4 a gig. That's pricey, not really consumer grade pricing,
right?
And it's not meant for that. To be very fair.
This is not a consumer product. Intel has said there will be one coming.
The idea was to bridge between the cost of NAND and the cost of DRAM, splitting the difference in performance and then splitting the difference in cost, and they appear to have done that.
Yeah,
right.
It sits pretty neatly between a good NVMe product and server class DRAM, and they even have a way for you to use this thing called memory drive technology, which you can just install this product in a server. And it has like this overlay software driver sort of thing that kind of turns it into a hybrid XPoint and RAM disk.
So the operating system can address the Optane drive as memory.
It's one big RAM pool that speaks to the system RAM as a cache layer and to the Optane as just storage, right?
So did it meet your expectations?
Yeah,
it did.
Met
Honestly, it wasn't like, oh, I thought it was going to do this or this or this.
No, I mean, if you went all the way back to the 2 years ago when people were saying 1000x and you didn't properly wrap your brain around what that actually meant.
Well, they weren't helping people wrap their brain around it, to be fair.
Right. But what you're looking at today is basically about as fast as you can push a PCIe NVMe thing.
All right.
Right? It's just there's not much more room to go without other changes in OS, how the kernel works and other things.
How long until we see the consumer one?
They said towards the end of the year.
Okay, so not that far.
I thought they were saying like late Q2.
Late Q2 is like June.
Sorry, late second half. Sorry.
Okay,
yeah,
right. That's like December.
For like, and I wouldn't be surprised if that actually slid towards the beginning of next year, because again, you lose potentially 50% of the benefit at the most extreme latencies just due to the way that operating systems work right now. So they need a good driver. A driver can
operating
fix this.
system fixes would be better.
Operating system optimizations, fixes and whatnot would be better. Yeah, so there's a little bit of other things that need to get shuffled around to see the full benefit, but they did say a consumer one's coming, like for your gaming systems.
Not the Intel Optane memory. We'll talk about that next week.
Yeah, that's different.
But that's very different. So
they're talking about a client version
it
of this thing.
So that is the Intel Optane SSD DC P4800X, everybody. Go to the review at pcper.com and check it out. There's a lot more detail, a lot of graphs, a lot of information. It will take a while to digest it, I think, based on how much data is there. But let us know what you think, and if you're excited for the consumer variant, and I guess how much you're willing to pay for it.
Yeah.
Probably not $4 a gig.
Yeah.
All right. See you guys.
See ya.
If you enjoyed this content, consider supporting in-depth technical content by contributing at patreon.com/PCPer.